There's two more objectives that we need to take a look at here in section 3.1. The first one that we're going to take a look at is how do we find the area of oblique triangles? At first on its face, this might not seem that difficult given that we've always had a formula for the area of a triangle. We've always had 1/2 the product of the base and the height, specifically the altitude, meaning the distance perpendicularly to one side from one of the vertices of our triangle. But the problem is that with a lot of the triangles we've gotten in the past, we've usually been given nice triangles, ones where at least one of the heights, one of the altitudes, was easy enough to find. Or we could find it through maybe some application of the Pythagorean formula or something along those lines. But what we want to give ourselves now is a way through trigonometry to find the area for any oblique triangle, so any non-right triangle. And actually, we're going to adapt something we've already used as part of our ambiguous casework when we were dealing with side-side angle triangles. If we take a look at some of the work that we've already used, we actually found a specific way to find the altitude for given sides and given angle measures. In this specific case, we're referring to the h that we found before. It might not have been clear, but that h was standing in place for the altitude, as I previously talked about in lecture 19. The idea being that we're measuring one of our side lengths against it to see if that side length is long enough or maybe too long, so we end up with two triangles. But the important part is that actually gave us a way to measure the altitude based upon other information and without needing to use any complex other formulas. In this case, with each of the two triangles that you see here, whether they're acute or obtuse, the measurement of our altitude, our height here, is given by the same expression. It's b times the sine of a. So in this case, it doesn't matter whether we're dealing with a as an acute or an obtuse angle. We can find the length here by simply making a right triangle. Take a look. We've forced a right triangle whose hypotenuse is b, whose side opposite a is h. So it would just follow that sine of a would be the opposite side over the hypotenuse. And if we solve for that opposite side, we get the expression h equals b times the sine of a. Even if we're obtuse, we're still creating, in this case, a right triangle, and our measure for angle A is still going to give us the appropriate length for h. So now we have an easily available means to find the length of this altitude for any given values, as long as we know one side length and one angle measure. And then once we know that, it's a simple matter of, okay, what other side length do we know to create a base? And then we can substitute in our standard formula, 1/2 the product of the base times the height. This gives us several different variations here. The first is using the one that we already have. Since our normal formula is 1/2 the base times the height, in this case, using the triangle we saw a moment ago in both variations, the height was given by b times sine of a, and our base, based on their orientation, would be c. So in this case, this gives us an exact way to find the area for each of those oblique triangles. 1/2 the product b times c times the sine of angle a. And you can actually rotate the triangle to use different bases, but follow the same line of reasoning to find two additional formulas. Area can also be written as 1/2 a times b times the sine of angle c, or 1/2 times a times c times the sine of angle b. The important part to note here is that it's always the same pattern. It's 1/2 times the product of two of our side lengths multiplied by the sine of the angle that is not opposite to either of those sides. So here you'll see b times c, and we're using angle A times b, and we're using angle C, a times c, and we're using angle b. That formula is the easiest way to find the area for an oblique triangle if this is the information that we're given. If we know two side lengths and one angle, we can work to go ahead and find our area. We'll talk about what happens if, say, for example, all we know is side lengths. Can we still find the area of a triangle? That's something we'll talk about in the next section. But for right now, this is dealing with a very specific set of circumstances. And it's going to be to our advantage to take a look at a couple examples and make sure that we feel comfortable working this out. So let's go ahead and tackle a couple after a brief little summary here. So this is something, again, that you're going to need to have sort of not necessarily memorized, but you should be familiar enough with the patterns themselves and knowing when they're used. When we're dealing with the area for an oblique triangle, and we know two side lengths and the sine of an included angle, they actually mention that here, which is nice. It's specifically the angle between these two 9 sides. We have our 3 different variations on the area formula. they mention a specific result down here, which is what if we were dealing with a case where the known angle A was 90 degrees, or angle C or angle B. It doesn't really matter. The important part is that in those cases, the sine of 90 degrees is always equal to 1. So our lengths for B and C are already going to be our base and height in the triangle as we're talking about it. Specifically in this case, B would be the length of the height and C would be the length of the base as it was originally. This happens when sine of 90 degrees, when our angle is 90 degrees, if H and B are exactly equal to one another. This is that special edge line case that we were talking about before when we were talking about solving a triangle. If for some reason our side length opposite of our known angle is equal to H, then that's a very special case. Don't see it too often, but it's just kind of a proof of concept to say, hey, this works backwards as well. We're not going to use it this much, but it's something worth noting. Instead, let's take an actual problem out for a spin here. In this case, we want to find the area for a triangular lot having two sides of length 90 meters and 52 meters and an included angle of 102 degrees. So the important part to note here is that because they've said it is an included angle, this is specifically the angle between these two side lengths. If we were to sketch a figure for this particular problem, it would look a little something like this. We have a specific side length that we already know of 90 meters. I'm not even going to try and make this look pretty. I'm just going to try and get this down on paper. We have another side length of 52 meters. And we know that the angle between them is 102 degrees. So we can imagine completing the lot by adding this third side. But in our case, we don't actually need to do that. All we need to do is identify that we have two side lengths and the angle included between them. So in this case, it doesn't really matter who we assign to be A, B, C, or D, but let's just say for the sake of argument that A is 90, C is 52, then this angle that's between them is angle B. So then we use the area formula, 1/2 A times C times the sine of this angle between them, 102 degrees. I should go ahead and leave this for just now since we're doing the general form, 1/2 A times C times sine of B, but then we can go ahead and substitute in our actual values. 1/2 times 90 times 52 times sine of 102 degrees. So from here we could go ahead and actually evaluate this, keeping in mind that it's going to give us an approximation here. So that's something we really need to point out here. This is not going to be an exact answer, this is going to be an approximation. The reason for that is our value for sine of 102 degrees is not going to be an exact answer. If we go ahead and round this to the nearest square meter, our approximation here is going to come out to 2,289 square meters. In this case, notice that because we're talking about area, we switched our units from being linear meters to square meters. That's something you always need to notice anytime we switch to talking about area. With any of the other area problems that you might encounter as part of the homework, you're always going to be working off of the same basic premise. I need to know the length of two sides and the measure of their included angle, and then from there it's the same pattern. 1/2 times the product of the length of sides times sine of that included angle.